इसे पास में अब नहीं
Okay, welcome to day 5 of circuits. I want to start off with some logistical items. I was just posting this to Blackboard as you guys were all signing in. I need each of you to provide me with some information pertaining to the lab kits that need to be delivered to you guys. Good afternoon. Oh, actually, one administrative item before we get to anything related to the course. I'm home alone with my Pomeranian today. My wife is out, and so my Pomeranian is a puppy. He's very cute, but very narcissistic, and so there will probably be some howling, and it's possible that I will have to actually pick him up at some point. So apologies in advance for any inconvenience. So that's number one. Number two is related to the post that I was, okay, I'm not the only one. That's hilarious. Yeah, it's pandemic life. We need to get the circuit kit to you guys. And so I provided the email address of Tariq, one of the course TAs. So I need each of you guys to send him an email with your name, and then answering 2 questions. Number 1 is whether you will be able to pick up your kits in person at Steinman Hall. I think hopefully about half of you will be able to. That'll reduce our shipping costs and labor. And then number 2, if you're not available to come pick it up at Steinman Hall, and again, the date is flexible, we can accommodate you guys. So number 2 is if you're not able to pick it up, you got to provide us with a full shipping address to which we can send it to you. So please do that at your earliest convenience so that we can start the process. No, was there a Google? I think I mentioned I was going to do a Google form. Yeah, I'm gonna edit this post. I don't think we need a Google form for this one. I think we can just do it the old. Also, I'm just trying to minimize. Okay. In the email, please indicate your name and whether you will be okay. I'm trying to think of the other administrative items I wanted to cover. That's the main thing. Other than my howling dog, is that I want you guys to send Tariq an email so that we can get the kits to you guys. We have a lot of time to do the labs this year because you have the kits at home, so you can do them at any time. There's no reason why we should do labs in a scheduled time period, especially since some of you are in different time zones. Everyone has their own preferred work schedules, and I'm going to try to come up with a way to make the labs more more engaging. Okay, with that, as always, if there's any questions, jump in. Otherwise, I will try to load up my slide deck. Oh, we have a question. Daniel, go ahead.
I do have a question, Professor. What's gonna be the details of picking up the kits? Is it like when are we gonna be able? Is it by the end of this month or by March? Like when? Because the thing is that I
So
don't know when I can come to the campus or not.
yeah, I was hoping to get it done around the end of this month, beginning of March. So like basically, let's say in the next 3 weeks, I'll say we don't need, or we don't even want everyone coming on the same day. That's going to be coordinated with you and the TA. And if you can't come to campus in the next 3 weeks, let's say, just write down your shipping address.
Okay. Thank you.
No problem. No problem. Okay, we were covering nodal analysis. We will continue with nodal analysis today and also start with mesh analysis. Someone's already had enough. Oh, wrong slideshow. PowerPoint. Lecture 3.
Professor,
Yes.
did you upload anything to Blackboard regarding the homework you said that you're gonna upload on?
No, yeah, I haven't done it. That's a good question.
Where are you gonna upload it? Are you gonna put a new file and name it homework so we can find it?
Yeah. First of all, there'll be an announcement. I'll never post a homework without a corresponding announcement. There'll be an announcement. There will be probably a new folder set up, like a new content folder, which will contain all the homework so that you're not going to miss it. And I'll mention it in class when it happens.
Thank you,
With
Professor.
me, sometimes you have to wait, although I don't think you guys really mind. But there will be homeworks. Again, I'm trying to, if time allows, I'm trying to make them different this year. I could just post the previous homeworks. But I would like to spice things up a little bit, make things more fun, if that's even possible. Oh, yeah, I don't know. Circuits can be fun. It's like a puzzle. A circuit is like a puzzle. That's the way you should think of it. So I think it is possible to make it fun. I think for many of you, it's going to be more fun with the actual lab, but nevertheless, I'm thinking about ways to make this. Ideally, what I would like to do, if there was like ideally a cloud-based software, like what I mean by that is a software that you operate just in a browser, nothing that requires installation files, that allows you to build a circuit and simulate it easily. We experimented with something last year, which was decent, but not perfect. Because then, I think that kind of a modern circuits course would have you doing a lot of work in software, just because that's how everything is done nowadays. Everything you would simulate any circuit that you would think about building before actually building it. But I haven't really found anything that fits the needs of this class, but I will keep looking. Okay. Share screen.
Thank you, Professor.
No problem. I will take a risk and do a slideshow. Okay, so I'll probably do just a quick recap. So with nodal analysis, there's a few steps. First, you define your node. So for example, in this circuit here, we have node 1, node 2, and the ground node. And that's step 1, is define your nodes. And then step 2 is to write your KCL equation. So for example, for this, so you will indicate in each branch of the circuit, you'll want to draw a current arrow. And direction is mostly arbitrary. And then once you have the current arrows, you'll want to write a KCL equation at each of the non-reference nodes. So in this circuit, at nodes 1 and 2, you'll want to write a KCL equation. So the KCL equation at node 1 is 1 amp is equal to I1 plus I2. And at node 2, the KCL equation is I2 flowing in is equal to I3 plus 4 flowing out. Then you substitute your Ohm's law expressions, you get a matrix, you get a system of equations. I'm trusting that you guys know how to solve systems of equations. You will not be tested on linear algebra. On the exams and the homeworks, you're expected to solve them, but you can solve them any way you want, including programmable calculators or Kramer's rule, which is not very popular. Okay. Now, did we, actually, I'm trying to think of where we left off last class. Can someone remind me whether we covered either problem 2 or problem 3?
We only finished problem 1.
Only finished problem 1. So what I'm going to do is there isn't enough time in the course to cover every example problem. So what I'm going to do, and since you'll have the solutions, we're going to proceed to circuit number 3. So I'm going to skip ahead. In the future, I could record myself solving all these, and then all the ones that we don't have time for, I could just post. Okay, so circuit number 3. So first of all, in this circuit, we have a few things going on. We have 3 non-reference nodes. So there's node 1, node 2, and node 3, right? Notice that everything here is, everything that I'm tracing with my cursor right now is all node 1. Everything that I'm tracing with my cursor here is all node 3. And everything that I'm tracing with my cursor here is node 2. So those are the only 3 non-reference nodes. The 4th node is at the bottom, it's the ground. So generally, the bottom of the circuit will serve as the ground node. We have also 2 current sources. One of the current sources is an independent source. It's 10 amps here at the bottom left. The other is a dependent current source. So this is actually a typo by the book. This symbol here should not be a circle. It should be a diamond. And it doesn't change anything for the solution, but the value of this current source is 4 times Ix, where Ix has been defined as the current flowing down the 4 ohm resistor here. So I've gone ahead and I've labeled the branch current. So this is I1 here. So this current arrow here, which is drawn a little bit too far down, corresponds to this current here, flowing from left to right. So I1 is the current flowing from node 1 to node 2. I2 is the current flowing from node 1 to node 3. And Ix is given to us. It's the current flowing down the 4 ohm resistor. And I3 is the current flowing down the 6 ohm resistor. Okay. So we have our nodes 1, 2, and 3. We have our branch currents I1, I2, I3, Ix. Now we should be ready to write our KCL equations. Okay, so let's start. I'm going to start you off with node number 1. I'm going to give you the base, and then I'm going to ask you guys to fill in I1 and I2 for me. So this equation says that 10 amps is flowing in, and I1 plus I2 is flowing out. Hopefully you all agree with that. Let me just mute myself because my dog is howling. Give me a second. Okay. Okay. Sorry. My dog is so funny. He likes a spot. He likes for me or anyone in the family to sit with him in the living room, and so he'll go to the living room and just start howling like, I'm right here. Anyhow, 10 is equal to I1 plus I2. And so who can tell me now the Ohm's law expression for I1? So remember, I1 is the current flowing from node 1 to node 2. Who can tell me the, oh, we had an answer in the chat, thank you. V1, yeah, so brackets around the V1 minus V2, right? I think that's probably what you meant. You probably knew that. I just wanted to make sure that, okay, so that is the expression for I1. And then for I2, which is here, it's V1 minus V3. Oh, sorry, this is what you were saying here. V1 minus V2 over 3 is I1. And then I2 is equal to V1 minus V3 over 2. So again, you're just applying Ohm's law. You're just looking to see the top node, the bottom node, and the resistor in between them. The top node, the bottom node, and then the in-between resistor. So this here, this term here, I wrote it backwards, I think. This term here is I2, and this term here is I1. And we can rearrange this just with some algebraic manipulation to get it into a form where you have integer coefficients for everything. So we have 5v1 minus 2v2 minus 3v3 is equal to 60. So now we have 3 unknowns and 1 equation. So we know we need 2 more equations. And then we also know that we're going to get those other 2 equations by applying KCL at the other 2 nodes. So who wants to take a shot at the KCL equation at node number 2, just in terms of currents for now? You can chat, you can use your microphone however you want.
If B for node 2 I1 plus 4IX equals IX.
Yes. I think I have 3 people all with the same answer. So the audio answer was, I think, correct, and so are the 2 answers on the chat. So yeah, so it's going to be I1 plus 4IX is equal to IX. And so that reduces, oh, before I show you that, I just want to, so I1, we already know what it is. It's V1 minus V2 over 3. We also need an expression though for IX. And so note that IX is just the current flowing from node 2 down to ground. And we know that the voltage at ground is 0. So IX is just going to be V2 divided by 4. Again, we can rearrange this and get it all in terms of integer coefficients. We have 4v1 plus 5v2 is equal to 0. So that's our second equation. And this is a nice equation because there's no v3. So this makes, if you want to go down the substitution route, this is a nice equation because you can just express v1 in terms of v2 directly without needing to consider v3. All right, so who can now help me with the KCL equation at node number 3? Again, and just in terms of currents to start.
Would it be I2 equals 4IX plus I3?
Excellent. I2 is flowing in, and that's the only current that's flowing in, and then 4IX plus I3 are flowing out. So we already know what the Ohm's law substitutions are. We did them previously. So we will just go ahead and substitute them. Oh, actually, there's one extra one that we didn't do I3 yet previously. So I3 is equal to V3 divided by 6. And that's because it's V3 minus 0 divided by 6. And again, we can rearrange to have a nice integer equation. And this is what our linear system looks like. So again, the way I like to solve these, and I'm sure the programmable calculators also do this for you. So you have your first equation is 5, -2, -3, and the coefficient is 60. The next equation is 4v1, 5v2, plus 0v3 is equal to 0. And the last equation is 3v1 minus 6v2 minus 4v3 is equal to 0. And so again, you can do this with Kramer's rule if you want, but it's not necessary. However you solve it, the answers are here: 4.8 volts for V1, 2.4 volts for V2, and minus 2.4 volts for V3. Okay, is there any questions on the solution to this problem? Okay. We now have to cover, so notice that in the example, in the two problems that we did for nodal analysis, we didn't have any batteries in the circuit. We did not have any voltage sources. We just had current sources, which made applying KCL very easy. Now, there's an extra step or an extra concept that needs to be introduced when applying nodal analysis to circuits containing batteries. And that's going to lead to something called a supernode. And again, I'll explain to you what that is. But first, let's break this situation into two cases. Case number one is if the voltage source is connected between a reference node and a non-reference node. So the reference node is the ground here, and there's two batteries in the circuit, battery 1 and battery 2. So this 10-volt battery does not pose a problem for us. Why is that? Because the battery is placed between the ground and a non-reference node, in this case V1, we know that V1 has to be equal to 10 volts, right? That's the definition of a battery. The definition of a battery is that it maintains a voltage, in this case of 10 volts, between its terminals. So if this terminal is by definition 0 volts, then V1 has to be equal to 10 volts. So this node you've already got a solution for. And so if a battery is connected between the ground and a non-reference node, that's not a problem. You just write down V1 is equal to 10 volts, and that's basically one of your three equations for this picture. On the other hand, if the battery is connected between two non-reference nodes, that's a different situation. Because here, it is not possible to come up with a KCL equation between V2 and V3, right? You can apply KVL between V2 and V3, but not KCL. There is no way of knowing what the current is that flows between nodes 2 and 3. So remember, if you think about what a battery does, right? A battery guarantees that it will maintain a certain voltage across its terminals. And it does that no matter what it's connected to. And so, just have a question. Yeah, so what is a reference node and non-reference node? So a reference node is just another word for ground, and the non-reference node is everything else. So node 1, node 2, node 3, and this. So a non-reference node is any ground, is any node other than the ground, basically. And so we don't have any way of knowing how much current will be flowing through this battery. And so we cannot easily write a KCL equation for it. And so what we do is we make a virtual node or a supernode. Another word for this generalized node. So we basically collapse everything that's in this dashed ellipse here into a single point. And if there's anything that's in parallel with it, we will also include that into the supernode. And so let me just make a couple of remarks. So in this picture, nodes 2 and 3 form a supernode. And what we'll do is we'll treat it as if it's just a single collapsed point in the circuit. And it will, this will, I think, hopefully become clear when we do a few examples. So first of all, why is it fair to do this? Why is this a legit operation? Well, it's a legit operation because you're not violating the fundamental laws of conservation, which are KCL and KVL. You basically, you know that if you think of this as a kind of one entity, the currents flowing into that one entity have to equal the currents flowing out of that entity, because we know that current cannot be charged, cannot be destroyed. Similarly, energy cannot be destroyed, and therefore there cannot be any loss of, KVL applied to this loop that I'm circling here still has to hold. And so what do we actually do with the supernode to get our equations? Well, the first thing we do is we will apply KCL at this ellipse. So notice that to this ellipse, we have I1 flowing in and I4 flowing in. So I4 is the current here. We also have I2 flowing out and I3 flowing out. So we have two currents in, I1 and I4, and two currents out, I2 and I3. So we equate those to each other. And then so this is the KCL equation at the supernode. So again, you treat this as if it was a single node and it has currents coming in and currents coming out. And those currents have to equal each other. And then you apply Ohm's law in just the same way as before. So I1 is equal to V1 minus V2 divided by 2. That's over here. I4 is equal to V1 minus V3 divided by 4. That's this term. I2 is equal to V2 minus 0 divided by 8. That's over here. And then I3 is equal to V3 minus 0 divided by 6. So another way, if you're not comfortable with the idea of a supernode, it's not tangible enough for you, just think about it this way. This current plus this current has to equal to this current plus this current. Why? Because you cannot just lose current in the battery. The battery cannot suck up or inject extra current. It has to obey the law of conservation of charge. But the supernode just makes it a little bit easier, I think, to write down these equations, right? So you collapse nodes 2 and 3 into a single node and then write your KCL equation. However, because we've collapsed node 2 and 3 into a single node, we now lose an equation, because now instead of having 3 KCL equations, we only have 2. And so we are missing one more independent piece of information. And that piece of information is going to come from KVL. So notice that in this picture, this is V2 and this is V3. And the presence of this battery between nodes 2 and 3 means that V2 minus V3 has to equal to 5. So you can also think about this as a KVL. So let's apply KVL going from the bottom left clockwise around this bottom right mesh. We have a voltage rise of V2. Remember, voltage rises are written with a negative sign. Then a voltage drop of 5. And then another voltage drop of V3. So the application of KVL to this mesh is minus V2 plus 5 plus V3 is equal to 0. In other words, V2 minus V3 is equal to 5, which you can easily see, again, just from this picture. We know that the difference between V2 and V3 has to equal to 5 volts because this battery is by definition producing a voltage of 5 volts between its two terminals. Okay. So now we do have three equations, right? So the first equation is KCL at node 1. The second, or is actually in this case equal to V1 is equal to 10. The second equation is this KCL at node 2. And the third equation is KVL around the supernode. And so the steps to apply nodal analysis in a circuit that has voltage sources between two non-reference nodes are the following, or not the steps, but rather the properties are that the voltage source inside the supernode provides a constraint to solve for the node voltages. You can think of the supernode, this ellipse, as not having a voltage of its own, but I never really found this statement helpful. And a supernode, this last point, number 3, is important. So whenever you have a supernode, you need to apply both KCL and KVL to it. So to do KCL, you draw an ellipse around it, and then you equate currents flowing in to currents flowing out. And to KVL is just, in this case, V2 minus V3 is equal to 5. And that can be thought of as the application of the voltage law around the loop that contains the supernode. Okay, let's do an example because my experience with this is that this becomes a lot easier when you actually see it in action, so to speak. I'll just take a sip of my water and continue.
Professor, what were the properties of the supernode? I didn't really have the chance to look at it.
So the properties are that it provides a constraint to solve for the node voltages. And so basically, the properties are that it's really a combination of two or more nodes. And that node, you can think of it as not having any voltage. It's just a point in a circuit. But these properties I don't really find useful. These slides, they're basically they're derived from the book, adapted from the book. But I think the third point is the important one, that when you form a supernode, you need to apply both KCL and KVL to it.
Okay, thank you.
Okay, you're welcome. Let's do an example. So we have this circuit where we have a supernode in between nodes 1 and nodes 2. And why is that? Because there's a battery between them, right? And so our job here is to solve for V1 and V2. So the first thing we're going to do, excuse me, the first thing we're going to do is draw a supernode. And because the 10 ohm resistor is in parallel with the 2-volt battery, we're going to include the 10 ohm resistor in the supernode. So we're going to kind of dash out this entire section of the circuit. Okay, so notice that this entire loop has been converted into the supernode. And now we want to apply KCL at the supernode. Notice that there are 4 currents involved. We have 2 amps flowing in. We have I1 flowing out, I2 flowing out, and 7 amps flowing out. So in other words, if you think about this dashed rectangular section of circuit, we have 1 current flowing in, that's the 2 amps, and we have a sum of I1 plus I2 plus 7 flowing out. And so that is the KCL equation at the supernode. And so we can apply our Ohm's law equations, which is that I1 is equal to V1 over 2, and I2 is equal to V2 over 4. Right? So this is, so again, I1 is equal to V1 minus 0 over 2, and I2 is equal to V2 minus 0 over 4. So now we can express our equation without fractions, and we can rearrange to solve for V2. So before I move on to the second equation here, is there any questions? Is there any confusion, comments about what was done here?
Excuse me.
Go ahead.
Can you go over why you put the 10 ohms and the battery in the same?
Yeah, it's a good question. And so notice that here we're interested in we know that there's 2 volts between nodes 1 and nodes 2. Now, the 10 ohm resistor also happens to be connected between those 2 nodes. And so, for example, I guess one way of answering is if you only, let me see, I'm going to take this off screen share if I can. Okay, hold on a second here. And show, would that work? Yes, okay. Imagine that we were to draw our ellipse only around here. And actually it will be more like that. Again, it's very messy, but that'll be our ellipse. That will create a problem for us because, you know, you have this current, you have this current, you have this current, and you have this current. If you don't include the 10 ohms, well, then you're also going to have this current and this current. So that's one reason why you have to include it. Another reason is that I'm going to try to use, yeah, maybe this one. The whole idea of a supernode is that it basically collapses a bunch of the circuit into a single node with a single voltage. So the 10 ohm resistor has the same voltage across it as the battery because it's in parallel. And therefore, it's valid to collapse it all because we know that the voltage across the 10 ohm resistor has to be the same as the voltage across the 2-volt battery. And so collapsing the battery and collapsing the resistor is the same thing. Now, if none of my answers speak to you, that's okay. As I said, I'm certainly not the world's greatest bioelectrical circuits teacher. You could just memorize the rule, namely the rule of supernodes is that where is it here? Where are the rules? I thought it was here. A supernode is formed by enclosing a voltage source connected between two different zones, and yeah, so it's this bottoms. So the rule is that if there's any 2 nodes that have a battery between them, anything that's in parallel with those 2 nodes gets lumped into the supernode. And so another way of thinking about this is that if you think about the ellipse here, the transparent ellipse. If you think about the currents flowing in and out of that ellipse, we know that that ellipse cannot just suck up any current or inject any current, right? So the currents flowing into this ellipse have to equal the currents flowing out of that ellipse. Now, if we, let me see, go back to the animations. If we made, sorry. If we made the ellipse here, you know what? I think this would still work. It's just that now you would have to include the current, this current flowing out and this current flowing in. So it's more, the answer to your question is more that we don't really have to do it, but we can do it and it makes our life easier. Because if this ellipse contains the 10 ohm resistor, it just becomes easier to write the KCL equation. All right. So that's a really good question. And I think it's a question that, or it's an issue that I think lots of students have a hard time with. But if if nothing speaks to you, just remember that anything that's in parallel with the battery gets lumped into the supernode. Okay.
Sir?
Question?
Yeah, so where in the KCL equation are we seeing the 10 ohms incorporated? Or
Yeah,
where
that's a
is
great question. We're not, because we don't have to. Because,
where's that?
do you understand? This rectangle here cannot suck up or inject any extra current. And so we know that if you think about this dash rectangle as an entity, currents flowing in has to equal currents flowing out. And so basically any current that flows into the 10 ohm resistor will have to come back out. So it's as if it would appear on both sides of this equation, and therefore we don't include it. Okay, so now we have the KCL equation for the supernode. Now we need to write the KVL equation for the supernode. And so I like to think about this just as a simple subtraction, namely V2 minus V1 is equal to 2. Right? So another way of doing it is to write a KVL equation from the bottom left here. So up V1, up 2, down V2. Right? So minus V1 minus 2 volts plus V2 is equal to 0, which is equivalent to V2 is equal to V1 plus 2, which is equivalent to what I said at the beginning, which is that V2 minus V1 is equal to 2 volts. So now we have 2 equations and 2 unknowns, and we can just substitute one into the other, solve, and get that V1 is equal to negative 7 1/3 of a volt, and V2 is equal to negative 5 1/3 of a volt. Notice that the 10 ohm resistor does not make any difference because it's connected across the supernode. So this 10 ohm resistor has a current across it, but it does not have it has the same voltage as the battery. So the voltage across this resistor is known to us, is just equal to 2 volts. So the current across it will just be equal to 1/5 of an ampere, right? So 2 volts divided by 10 ohms. So there will be 2 amps flowing this way here, like this. All right, let us do some examples. So let me try to think. Let's do again. Let's skip the middle example. Oh, a chat question. Yeah, no, yeah. So the reason that it's the reason, let me see. Notice the polarity of this battery, the negative sign here and the positive sign here, right? So the battery is in the opposite polarity as you're used to seeing. Usually you see the plus sign here and the minus sign here. Okay, good, great. Let's move on to this circuit. So in this circuit, by the way, this is a 3-volt battery, and again, notice the polarity here. So first of all, how many nodes are in the circuit? How many unique nodes are in the circuit? Very good. Excellent. Or yes, it is. It is 4. Yeah, I had a brain cramp. So it's 1, 2, 3, and 4. Right. Now, notice that what is the voltage at this node here that I'm pointing to?
7.
7 volts, exactly. 7 volts. And so we don't need to solve for the only two nodes that we really need to solve for are this one and this one, because this is by definition 0, and this is, we know that this is 7. So let's define our node voltages. So V1 is equal to 7. V2 is equal to V. So notice that, again, this picture is a bit cluttered. Hopefully it's not too confusing, but I've equated V2 to V. Why is that? Because this is 0, and there's a voltage rise of V up to this point. So in other words, the voltage at this point is equal to the voltage across this 3 ohm resistor. And then we will call this node here V3. And I've also gone ahead and said that that voltage is equal to 2 times I. So why is that? Why? Because Ohm's law says that the voltage drop across the 2 ohm resistor is equal to 2 ohms times I amps. And so since this is 0 volts, and since the drop across this resistor is 2I, the voltage here has to be equal to 2I. All right. So we have voltages of 7, V, and 2I. And we also have some branch current. So this, we'll call this current here I1. We'll call this current here I2. And we'll call this current down through the 2 ohm I. And we'll call this current I3. So there's a lot of variables here, which makes this problem look more difficult than it actually is, because this really is just a 2-node problem. So now what we want to do is figure out, where is there a supernode? Well, the picture has it labeled with the with that rounded rectangle. So the supernode is in between nodes 2 and node 3. So we need to define a KCL equation and a KVL equation for that supernode. So let's start with KCL. So we know that I1 is flowing in, and then the other 3 currents are all flowing out. We have I2 flowing out, I flowing out, and I3 flowing out. So if you consider this rectangle here, only I1 is flowing into the rectangle. The other 3 currents are all flowing downwards, away from it. So we have I1 is equal to I2 plus I plus I3. I can't tell if I'm getting a call or if one of you is getting a call. Let me just see. I don't think it was me. Though we'll never know. All right. Yeah, so now the next step is to substitute our Ohm's law expressions into I1, I2, and I3, right? So notice that I1 is the current flowing from V1 to V2. So the current is equal to V1, which is 7, minus V2, which is V. So 7 minus V divided by 4. Okay, so this here is just a consequence of Ohm's law from this point to this point. I2 is by definition equal to V over 3, because the voltage across the resistor is V and the resistance is 3 ohms. And so the current flowing down here is V over 3. So this is just I, which we'll keep as is. We don't have to we don't really have to label as anything. It's kind of labeled for us in the circuit. And then finally, I3, which is the current flowing down the 6 ohm, is equal to 2I divided by 6. And why is it 2I divided by 6? This may confuse some of you because you're used to multiplying currents by resistors. Here you're dividing a current I because this current 2I is actually a voltage, right? I is the current, 2I is the voltage at this point. And so V3 is equal to 2I. And therefore you divide V3 by 6 to get the current through the 6 ohm resistor. In any case, we have an equation here that has two variables. What happened to I? I is given to us in the problem.
Never mind. Sorry about that. I missed it.
That's okay. All good. Now we're going to go ahead and apply our KVL equation across the supernode. So who can tell me a KVL equation for the supernode here? So what is this voltage here equal to? Let me just see. V minus 3 is equal to 2I. V3, let me just check. So let's see. V, so I would say that 2I minus V would be equal to 3. So this is almost right. And then let me just check this one. V3, so V2I. Yeah, I think the second one is right. So I write it as this, V3 minus V2 is equal to 3. So in other words, 2I minus V is equal to 3. Because V3 is equal to 2I and V2 is equal to V. Okay, so here is the KVL equation. We start from the bottom left, so we go up V, up 3 volts, and then down 2I volts. So again, you can reduce this all into 2 equations and 2 unknowns, and the 2 unknowns here are I and V. So now we have 2 nice linear equations. We can combine them into a single equation. We can just substitute. Let's see what the substitution here was. We substituted V for I. So I think what I've done here is I've substituted this equation into this one to arrive at this. And I'm gonna gloss over the algebra because again, this is not an algebra course. We know that you're all capable of solving arithmetic equations, and so we will just get to the solution, which is that V is equal to negative 0.2 volts and I is equal to 1.4 amps. And so there was nothing new in this equation. The only reason it looks a bit different is because we had a branch current labeled to us, given to us with this variable I here. But at the end of the day, this is just a 2-node system of equations, V2 and V3. It's just that here, instead of calling them V2 and V3, we call them V and 2I, but it's all the same. Okay, I'm gonna skip number 2. I'm gonna let you go over it on your own time. And again, if I have time, I would love to record each of these into a little video, but I haven't done it yet. Okay, so we're gonna go ahead and do, right, and actually, okay. So here's what so let me actually change course on that. This problem, I don't like this. I'm gonna actually do question number 2, I think. Yeah, I'm gonna do question number 2 because question number 3 is one that I usually say, I usually kind of pose it as a bonus problem for students. There is a solution to it on the slides, but it's I don't like the solution, and I invite each of you. So just to be clear, so which question I'm talking about. So this will be on, for me, this is slide number 23. It's the question on the bottom right. So this is a question that has 2 voltage sources in it. And so if you want to come up with a solution to the problem of your own, by all means, go ahead and try it and submit it to me. And if I like it, I'll give you bonus points. That's always been my policy for this course, because this is a tricky problem. And so what I'm going to do is I'm going to not present it in class. I'm going to leave it as a bonus exercise for you guys. I will, on the other hand, do example number 2. So not all these are not great problems. Yeah, email it to me. You have to solve, so to get the points, you need to solve for V1, V2, and V3. So you need to provide a solution for the node voltages. And I have had people actually get the points for it in the last couple of years. Okay. So the questions like these is when I really wish that I had a board, and maybe I should buy a board and just find a high resolution camera or something. But for now, we are stuck with the system. Okay, so this is a circuit that has 4 nodes, and the nodes are labeled 1, 2, 3, and 4. And there are 2 supernodes in this circuit. There's a supernode between nodes 1 and 2, and there's another supernode between nodes 3 and 4. So we know that to solve this problem, we're going to need 4 independent equations because we have 4 unknowns. And so the 4 equations are going to come from, I mean, there's actually more than one way of solving this problem. But if you do KCL and KVL at each of these supernodes, you will get your 4 independent equations. So let's start off with the supernode here between 1 and 2. Let's see if I have, yeah, oops, close this. So before anything, what we need to do is to label our branch currents. So I1 is going to be the current that's flowing upwards from node 1 through the 3 ohm resistor and down to node 4. I2 is defined as flowing from node 1 to ground. I3 is defined as flowing from nodes 3 to node 2. I4 is defined as flowing from node 4 down to ground. And I5 is defined as flowing from node 3 to ground. And so now we have all our nodes labeled, 1, 2, 3, 4. We've collapsed our supernodes, right? So there was the 20 volt supernode has been collapsed here, and the 3VX battery has been collapsed into this supernode here. So these 2 ellipses represent the 2 supernodes in this problem. And the reason that these 2 are supernodes is because they are batteries that connect 2 non-reference nodes. So first of all, is everyone clear as to this picture here? Because that is a starting point for the solution.
Question.
Yeah.
It doesn't matter that it's dependent voltage source at this point, right?
That's a good question. It doesn't matter because the dependent voltage source still has to obey KVL and KCL. It doesn't change the fact that any current entering this ellipse has to exit at the ellipse. So absolutely right. Yeah, the fact that it's dependent doesn't change how you treat it with the supernode analysis. Okay, so now we can proceed. We can start to write down our 4 equations. So who can take a shot at the KCL equation at this supernode?
Is it 10 plus I3 is equal to I1 plus I2?
Yes, that is exactly right. 10 plus I3 is equal to I1 plus I2. This is flowing in, this is flowing in, and then the 2 currents flowing out are the I1 and the I2. And what about, now we need to substitute I1, I2, and I3 with voltages. So what is going to be the Ohm's law expression for I1?
Is it V1 minus V4 over 3?
Excellent. It is V1 minus V4 over 3. What about the Nodal's law, the Ohm's law expression for I2?
V1 over, V1 over 2, yeah.
Excellent. What about the Ohm's law expression for I3?
V3 minus V2 over 6.
Excellent. Okay, so now we can plug those in. And we have 1 equation with 4 unknowns. So we still need 3 more equations, but we're a quarter of the way there. All right. Let's see what to do next. Let's do I can't remember the book's order of solution. Let's do the KVL equation at the supernode. So who can tell me the KVL equation at the left supernode? So let me just answer, Hannah, your question. The question is, do we ignore the Vx on the 3 ohm resistor for now? So we haven't really ignored it, right? This I1, oh, you're saying, I see. Yeah, so, right. So Vx is labeled as the voltage across the 3 ohm resistor. So Vx is really equal to V1 minus V4. And you'll see later that there is a substitution that's going to happen. So this V1 minus V4 is equal to Vx. But you could have written this equation with Vx instead of V1 over V4 and still gotten to the right answer. But let's just, for the sake of sticking with the node voltages explicitly given to us, let's just write the voltage across the 3 ohm was V1 minus V4 for now. But it would have been correct to replace the V1 minus V4 here with Vx. But that would have introduced a kind of a 5th variable. Okay, what was I asking? I was asking, yeah, what's the KVL equation at supernode 1, 2 here? Okay, so
Is it 20 equals V1 plus V2?
almost. It's 20 is equal to V1 minus V2, right? So if you want to do Ohm's law, it would be like minus V1. I'm putting this in the chat. Plus 20 plus V2 is equal to 0. sorry, everyone. So in other words, V1 minus V2 is equal to 20. So for me, I just always look at the difference between the voltage difference between here and here is 20 volts. That's always the way that I do process it in my head, but everyone's got a different style. So however you want to do it is fine. Okay, so the book has jumped ahead to supernodes 3 and 4. So what I will do is I'll just go over that because you already see it on the screen. I'll just go over how they got this. So they went ahead and wrote down the KCL equation for supernode 3, 4. So again, there's one current flowing in, and that's I1. So notice that this ellipse has one current flowing in and 1, 2, 3 currents flowing out. Okay, so the currents flowing out are I3, I4, and I5, and the currents flowing in are I1. So again, you just replace each of these with the Ohm's law. So notice that I1 is still the same, V1 minus V4 over 3. I3 is still the same, it's just V3 minus V2 over 6. Sergio, I'll answer your question in just a second. I5 is equal to V3 minus 0 over 4. And then I4 is equal to, I5 is V3 over 4 and I4 is V4 over 1. Okay, so the question is, why is it negative V1 again for the KVL for the first supernode? So imagine, okay.
Can we draw the, you know how for the other questions we did that, the box thingy with the nodes? Maybe we
Yeah.
can do that to explain it.
Exactly. Thank you. Yeah, that's, I'm gonna draw this. So and then super and the current is going this way. So that's supposed to be a circle. The current, so that it's negative V1 plus 20. I love my kindergarten handwriting for this. Plus V2 is equal to 0. Yes, it's voltage rises get labeled with a negative.
I have another question now.
Go ahead.
The place that has 10 amps as the current. So doesn't current flow from the positive to the negative, or the?
Yeah, it's a great question. So notice that this V2, this is just the answer to this question. V2 will probably come out negative, right? So V2 is just a variable that can have a positive or negative value when we solve for it. So the current is flowing. Oh, sorry, was that your question, or is your question related to the fact that, yeah, so basically if this is 0 volts here, this voltage here will almost surely be negative, right? Otherwise, you can't have 10 amps flowing from here to here.
Okay.
Okay, but that's a really good point. Okay, back to slideshow. Okay, so I think so we are over here. So this is, so V1 minus 20. It is the same. It is the same. You can multiply, sorry. Yes, it is the same. You can multiply left and right side by -1 and it doesn't change anything. So those, if you multiply everything, okay, good. So we were the first KCL. Yeah, so the first KCL, this is the best picture here to understand it. Notice that into this ellipse, we have one current flowing in, and we have two currents flowing out. Or sorry, my bad. I just confused you even more. We have two currents flowing in, 1 and 2. So we have 10 amps flowing in plus I3 flowing in. That's over here. And then we have two currents flowing out, I1 and I2. Right. So into this ellipse, sometimes you have to stare at it for a few seconds to see how many currents are entering or exiting that ellipse. And so the ones that are exiting are I1 and Y2, and the ones that are entering are 10 plus I3. So now we have another equation in V1, V2, V3, and V4. This is the step from here to here is just algebra, so I'm not gonna derive it. Okay, let me see what the book has next. Now we do the KVL equations, which we already started doing, right? We said that negative V1 plus 20 plus V2 is equal to 0. In other words, V1 minus V2 is equal to 20. And similarly, we have this KVL equation here, which is that minus V3 plus 3Vx plus V4 is equal to 0. So the problem is that Vx here introduces a fifth variable. We don't want that extra variable. We want to replace it with something that we've already we've already covered. And so notice that Vx is equivalent to V1 minus V4. Right? And so to see that, notice that this point here is V1 and this point here is V4. And Vx is defined as the difference between V1 and V4. So hopefully everyone is clear on this. And then if you substitute this into here, you get the 3V1 minus V3 minus 2V4 is equal to 0. So now we have enough information to solve the problem. We have 4 equations and 4 unknowns. But if I recall, the book goes through an extra step, which is not necessary, but I will do it. You can apply KVL to this loop here, to the top loop, to get an extra equation. Right, so it's plus Vx minus 3Vx plus 6 times I3 minus 20 is equal to 0. So again, try not to screw this up. We are going this out of the way. We are going this way. Right? That's over here, right? So you start off always at the bottom left, and you label a voltage drop with a positive sign and a voltage rise with a negative sign. So the 3Vx is a voltage rise. The 6I3 is a voltage drop. And the 20 volts is a voltage rise. Okay.
You wouldn't call that a super node, right?
Referring to which node?
To the one that is the loop 3
Yeah.
segment.
I wouldn't because there's no battery that's directly connecting nodes 1 and 4, right? The batteries are connecting nodes 1 and 2 and 3 and 4, but there's nothing connecting. There's no battery up here, for example. Okay, so now the book goes through, the rest of the solution is just doing solving the system of equations. I'm gonna skip it because I wanna move on to mesh analysis, but basically what the book does here is they reduce a 4-dimensional system of equations. They eliminate one of the variables. They eliminate V2. They write V2 as V1 minus 20, and everywhere where there's a V2, they replace it with V1 minus 20. And what that gives us is 3 equations and 3 unknowns. So this is equation 1, equation 2, and equation 3. So that turns into a system of 3 equations, which is easier to solve, but I'm gonna spare you of the Kramer's rule. And I'm going to skip over the bonus problem because it's a bonus for you. Hopefully some of you guys end up solving it. We will move on to mesh analysis. Give me just 1 second. So nodal analysis is a technique for solving, for applying KCL at every node in the equation. Mesh analysis, here we go. Sorry, I just wanted to, okay. So mesh analysis is kind of the complementary technique. It's the technique that allows us to solve for currents instead of voltages. So instead of solving for node voltages, we're solving for branch currents. And so what you're going to see is that mesh analysis is just the systematic application of KVL to a circuit. So our variables now become mesh current. So when I say mesh, it's really just like a rectangle or a square. So it's like a closed loop through a circuit. So a loop is a closed path with no node passed more than once. And a mesh is a loop that does not contain any other loop within it. Okay, so nodal analysis applies KCL to find the unknown voltages in a circuit. Well, mesh analysis, that was what we just did. Mesh analysis applies KVL to find the currents. So there's one detail which is really not important, but I'll just cover really quickly. This technique of mesh analysis only applies to planar circuits. So in other words, it only applies to 2-dimensional circuits. So for example, something like here, you cannot apply mesh analysis to. Because it's a 3-dimensional circuit. Circuits do exist, but we don't cover them in this course. We only cover circuits that can be drawn in 2 dimensions. So anything that requires a 3rd dimension, if you ever encounter it and you think to yourself, I want to apply mesh analysis, don't do it. That's all I'm going to say to it. In this class, we only consider 2-dimensional circuits, so it's really not consequential at all. Okay, so a mesh is a loop which does not contain any other loops within it. So what does that mean? What it means is that this is a mesh and this is a mesh, but this is not a mesh. In other words, ABEF is a mesh, BCDE is a mesh, but ACDF is not a mesh. Okay, so this is a mesh. This is, I mean, it's not a hard concept. I'm just gonna assume that you got it. We are interested in applying KVL to each of these meshes. So it's what you've been doing before. You're gonna start at the bottom left and you're gonna work your way clockwise. And this direction here, this clockwise arrowhead, just denotes the direction of positive current flow. There's only one new thing in with this technique that we haven't covered yet, and that is a distinction between a mesh current and a physical branch current. So in some cases, so the mesh current, by the way, is denoted with a lowercase, and the physical current, so when I say physical, I mean that's the actual current that's flowing in this branch. When I say mesh current, that's just a variable in our solution. It's not actually a physical thing. There's no, there's no physical little I1 or little I2, but there is a physical big I1, big I2, and big I3. So we're going to apply KVL to each of these two meshes. And here are the three steps. The step number one is to assign mesh currents to the end meshes. So we've already done it. This is mesh current I1, and this is mesh current I2. A supernode would not be considered a mesh. Oh, it has to be like a complete path for it to be considered a mesh. So when we did the KVL for the supernodes, we kind of had a mesh there. But the supernode by itself is not a mesh. It's just a branch. Why do we use lowercase in the last problem? Does it just change when doing these types of problems? Yes, in general, it changes, unfortunately. There's a lot of places where kind of, not really the rules change, but the conventions change. And so you can think of it this way. Capital I generally denotes a constant, and lowercase I generally denotes variables. That's like, that convention holds true across a lot of engineering. Even in computer programming, whenever you define a constant, you usually use uppercase and lowercase is variable. Last problem, the current was flowing counterclockwise, but we still had clockwise loop. Let me just take a look. Let me take a look at the last problem. So we had all these loops are drawn as flowing clockwise. But you're saying that the current was flowing counterclockwise. So do you want to, you can explain your question on chat if you want, or you can just chime in.
Can you go back one more slide? I
Yeah,
think
sure.
right there. No.
Yeah, sorry, I'm gonna get because it's animated.
Okay, right there. You had I2 going down and then the 10 amps going up. So wouldn't that be counterclockwise?
Isn't that why we had negative V1? Which would
Yeah,
make
Or is
so
that the extent?
I understand. So I understand the original question. Yeah, so right. So your question really gets at the heart of the difference between what a mesh current is not a physical current. It's just it actually doesn't even exist. There's no such thing as a mesh current actually physically. It's just a tool that we use to help us solve for the actual currents. And so where were the currents drawn? So like in this, if we didn't label any currents here. So basically, if we defined a mesh current here, let's say that we labeled I mesh as going clockwise, its value would probably be negative because the 10 amps, like you said, is flowing counterclockwise. But let me just, I think the answer to your question will become clearer. Yes, positive. So current flows from positive to negative. I mean, that's the convention that we make. Basically, let me just, at the heart of this, I really like to think about things in first principles when possible. Let me just get it to the blah, 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 blah. Okay. If you think about why was current flowing negative? So go ahead and tell me where you think the current was flowing from negative to positive. So Kuzema, can you explain where, yeah, so the voltage here, if you're talking about here, if this is 0, the value of V2 can be negative, right? So a voltage can be positive or negative. Same thing with a current. Only resistance has to be positive value, but the voltage can be negative. So if this is 0 volts and this is minus 10 volts, the positive 10 amps is still flowing from positive to negative, if that's what you were referring to, but I'm not exactly sure. Basically, think about it this way. Equal charges repel, unlike charges attract. And so what that means, and actually I hope I don't screw this explanation up. Generally, as a teacher, it's not a good idea to come up with spontaneous explanations. Let me find some okay, I'm gonna animate this. You have some ions. For now, just picture them all as being the same size. This isn't going to work, I don't think. Oh yeah, it is going to work. It's totally going to work. Okay. So there's a distance here between these two nodes. So in this configuration, this area here has more positive charge than this area. This has a net positive charge of 1 atom, and this has a net positive charge of -1 atom. So what's going to happen here? Well, nature likes things to be in balance, right? So this ion is going to flow over to this side, because then both sides will be at 0 charge. They'll have a 0 net charge. So that's why we say that positive charge flows from a higher voltage to a lower voltage, right? So it goes from positive to negative. And that's all that happens in reality. Is that charges will move themselves so that basically the charges will redistribute themselves so that everything is balanced. So that's all. And so you can think of in this course we think about positive charges doing the moving, but you can equally think of the negative charges as being the ones that move, and it doesn't change anything. Okay. Let me see if I can figure out where I was. I think I was here. Okay. Animate. Slideshow. Okay. So this is our picture here. I actually wanted to go through the steps again. So step number 1 is to assign mesh currents to each of the two meshes, each of the meshes. So here we have 2. We have mesh current I1 and mesh current I2. Step 2 is to apply KVL to each of the end meshes and then use Ohm's law to express the voltages in terms of the currents. And then step 3 is to solve the equation. So this course is really about steps 1 and 2. Again, we assume that you know how to solve systems of equations. So we're going to apply mesh analysis to this circuit. Now in this circuit, the V's and the R's are given as variables. In a problem, the V's and the R's will be given to you. But here the book likes to be super generic, and so we just have variables for the voltages and the resistances, but you can just imagine that they're actually numbers. Okay, so we have I1 and I2. So we define mesh current 1 and mesh current 2. And the second step is a critical step. We apply KVL. Okay, so KVL is negative V1 plus, so there's a voltage rise from here to here of V1, so we label it with a negative sign. And there's a voltage drop here of R1 times little I1. And then there's a voltage drop here of R3 times I1 minus I2. And this is where everyone gets confused, and that's okay. Basically, why is this current, why is the voltage drop from here to here equals to R3 times I1 minus I2? Why is it just not equal to R3 times I1? Well, the reason is that this mesh current lives in all branches that belong to the mesh. And this mesh current lives in all branches that belong to this mesh. Notice that the middle branch here with the R3 is property of both meshes. So this branch is shared by meshes 1 and 2. And therefore, the current flowing from B to E is equal to I1 minus I2. So why is it I1 minus I2? Why is it not I1 plus I2? Because I1 is flowing in the direction of the KVL, but I2 is flowing opposite the direction of KVL. So I'm going to stop here because I want to give you guys the opportunity to express your confusion if you're confused as to how we obtain this equation. All right. No questions. Maybe because everyone's tired. Don't worry, we're almost at the end of class. So for mesh 2, it's going to be very similar, right? We have R2 times I2 plus V2, right? This is a voltage drop of R2 times little I2 from here to here. From here to here is another voltage drop of capital V2. And from here to here is a voltage drop of R3 times I2 minus I1. So why is it I2 minus I1? Well, because in this case, when KVL is going in the direction of my cursor here, I2 is going with the direction of the KVL, where I1 is opposing it. Right? Yes, mesh 1 minus mesh 2. So the current from here to here, from E to B, is actually I2 minus I1. About big I3? So I3 is still here. So I3 is just equal to and so and the reason we do this is because you can think of this as a way to instead of dealing with 1, 2, and 3 currents, we're now dealing with 1, 2, and 3 variables. We now have 1 and 2 variables. So this has allowed us a way to reduce the number of variables in our system of equations. And so physically speaking, I3 is still there. Whatever, at the end of the day, we're going to get a value for little I1, and we're going to get a value for little I2. And big I3 is just going to be the difference between those two numbers. So we subtract mesh currents whenever we have a branch that belongs to more than one mesh. Okay. So the nice thing is that now we have a nice system of equations. So notice that this is equation number 1. And so this is the first coefficient, R1 plus R3. Minus R3 is the second coefficient. And then again, this minus R3 is the coefficient multiplying I1. And the R2 plus R3 is the coefficient multiplying I2. So again, we're left with 2 equations and 2 unknowns. The 2 unknowns here are the mesh currents. And the R's and the V's will be given to us. So we need if a circuit has n nodes, b branches, and l loops, then the number of loops is equal to the number of branches minus the number of nodes plus 1. If it doesn't make sense to you, don't worry about it. Basically, it just means that the number of loops plus the number of nodes minus 1 is equal to the number of branches. But it basically means, like, the only thing that matters here is for every mesh, you need one equation. Okay, so in the previous example, this was the relationship between the physical currents and the mesh currents. The mesh currents are like virtual. They don't exist. They're just variables in our mathematical analysis of the circuit. Okay, so let me just see if I can get through this example, and then hopefully it will make more sense to you once you see numbers. So here we have a circuit with two meshes, mesh 1 and mesh 2. So we're going to write the KVL equation for mesh number 1. So we have -15. So we're going to start off on the bottom left. We go up 15 volts. So we indicate a voltage rise with a minus sign. Plus 5I1, right? 5 little I1, because that little I1 is going, is getting multiplied via Ohm's law by the 5 ohms. So 5 little I1 is a voltage drop from here to here, plus 10 times I1 minus I2. So the voltage drop from this point to this point is equal to 10 ohms times the difference between mesh current 1 and mesh current 2. So notice again, the mesh current 1 is going with the flow of KVL, while mesh current 2 is going opposite to it. Plus 10, because there's a voltage drop at the end here. And that has to equal to 0. That gives us a nice equation for mesh number 1. For mesh 2, we apply the same procedure. Let's start at the top left here. 6 times little I2 is the voltage drop from here to here. Plus 4I2 is the voltage drop from here to here. And now what about the voltage drop from here to here? Well, this is a voltage rise of 10 volts, so we indicate that with a minus 10. And then the drop from here to here is equal to 10 times I2 minus I1, right? So this term here corresponds to this. This term here corresponds to this. This term here corresponds to this. And this is the voltage drop from this point back to the origin. And that gives us a second equation. So now we have a really nice 2x2 system, which we can solve simultaneously to get values for I1 and I2. So I am confident that mesh analysis will make sense to you once you've done enough of these problems. Basically, the only thing that you have to keep straight is that when you're doing the KVL equation and you come to a branch that is common to two meshes, you have to treat that branch current as a superposition of the two mesh currents that are involved. So for mesh 1, the current flowing down here is I1 minus I2. For mesh 2, the current flowing up here is I2 minus I1.
Professor, I
Okay.
have two questions.
Go ahead.
I understand mesh 1 because I1 branches to I2, so I get that you would subtract it if I was to make sense of why we're subtracting I1 from I2. But I don't get why we subtract I2 from I1.
Yeah, it's because if you think about the mesh here, let's pick a color. The mesh here, the KVL, it's not really that it's more that when you get here, this becomes the positive and this becomes the negative. So in this picture, I2 is going up This is I2. And this is I1. And so the reason is that the KVL as viewed by this resistor, the KVL is going in the opposite direction. In the first mesh, the KVL is going down the 10 ohm. In the second KVL, the current is going up the resistor, if that makes sense. So it has to do with polarity.
Oh, that makes sense. That makes sense. But so we don't use the capitalized I1, I2s, and I3s?
You don't use them. You can solve for them at the very end, but you don't use them in the mesh analysis.
Okay, understood. Thank you.
You're welcome. Okay. Right on cue, my battery is dying. I will see everybody back here on Monday for day 6 of the course. I wish you, yeah, you got a question?
Oh, yeah.
Go ahead.
When are your office hours?
Oh, yeah, let me post those right now. They're gonna be, let's see. They're gonna be on Wednesdays. I'm gonna make a note to myself to post those on Blackboard. Thank you for reminding me. Okay. Solution slides. I'll post them after this course, Kuzema. Okay, I will see everyone back here on Monday for day 6.